Hello friends, and I welcome you all in the lecture of Digital Electronics and Microprocessors. In previous lecture we have gone through the process of designing the combinational circuit. Then we have completed the concepts like half adder, full adder, half subtractor and full subtractor, wherein for each of the combinational circuit we have prepared the truth table. From the truth table, the K-map building has been completed, and based on the reduction obtained by using the K-map, the logical circuit for that combinational circuit we have defined out. In our today's lecture, we are going for the concepts of
Hello, friends.
we are going for the concept of the magnitude comparators and the parallel adders. So let's start with today's concept. So the parallel adder, as the name indicates, it's mainly going to give us the addition in the parallel form. That means if I'm having a multi-digit number as indicated over here, A and B, which are consisting of each 4-bit values. So this is called as a multi-digit number. So in such like this multi-digit number, all the bits will be added simultaneously when we are using the parallel adders. And to do the operation in the parallel adder, corresponding to every digit position, a separate full adder will be provided. So let's say for the first bit, the separate full adder, for second bit, separate full adder, third bit and for fourth bit also, the separate full adders will be given. But the necessity requirement for this operation of parallel addition is that initially the two inputs of addition should be saved in the separate registers which may be named as A and B for that full adder. When the parallel addition process is done, in the parallel addition process, for each of the sum operation, the output of adder will be routed to the appropriate bit of the sum register. That means here, along with the two input register, one another register named as sum has to exist, and that sum register is going to take all the additions values which are done parallelly. In the parallel binary adder, the output will be generated immediately after we are providing the inputs. But for the parallel adders, on one drawback is existing, and that drawback is said to be the carry propagation delay. Because until and unless I am doing the addition process, we cannot comment on what will be the carry generated for the next bit addition. And that's why here, until and unless the previous bit carry will be get generated, we cannot carry out the full adder operation for the next bits. And here this delay will be causing due to the propagation of the previous bit addition carry to the next stage. And so the next type of parallel adder will be needed, which is going to speed up the process, and that will be known as look ahead carry addition. This look ahead carry addition is going to eliminate the ripple carry delay. But before going for that ripple carry delay eliminating block of look ahead carry, we will see here the block diagram for the 4-bit parallel adder. So you can see here there are 4 different full adders which are present, and for every full adder a single bit from each of the number has been provided. So here B0 A0, B1 A1, B2 A2 and B3 A3, those have given as an inputs. But we will see now the carry inputs. The carry input for your first full adder, which is going to add the least significant bits, will be having value as 0. But with this all full addition operation of C0, A0 and B0, C1 will get generated, which is going to be propagated to the next full adder, which is going to add A1 and B1 values. With these three values of C1, A1, B1, the full addition operation will be done. S1 will be generated. At the same time, the C2 for the next bit addition will get forwarded from the previous addition to the next bit addition. Now C2, A2, B2 will be taken by the full adder 3, some S2 will be generated, and the next carry it is going to forward to the full adder 4 in the form of C3. And here C3, A3, B3 will be added to generate the sum of S3 and gives out the carry as C4 value. So let's go for the next concept of 4-bit carry look ahead generator. But actually this carry look ahead generator is one of the block of 4-bit parallel adder where the delay caused due to the propagation of carry is going to be eliminated. So in this case, first we will go for the block diagram change of that 4-bit parallel adder. As in case of previous parallel adder, a separate full adder will be provided for getting the addition of individual bits from the two numbers will be given out. And for these full adders, in previous block diagram, we have seen that carries are propagating from the previous addition full adder block to the next block, such as C1 forwarded, here C2 has been forwarded and here C3 has been forwarded. But if we are observing for this block diagram, such like this carry propagation from the previous full adder to the next full adder is not observed at any stage of addition operation. Instead of that, a below block which is mentioned in pink color named as 4-bit carry look ahead generator is present. And that's how here it is going to do the fast addition operation, and it will improve the speed by reducing the amount of time required to determine the carry bits. And this is how it is going to reduce the time which are delayed at each of the stage. So let's see how this whole process works logically. So in this part, for every full adder circuit, we will have the two logical operations are going to be seen. One is said to be the carry generation and another one is said to be the carry propagation. This carry generation and carry propagation, as shown in this previous diagram here, which are the outputs of look ahead generator block, they will be generated as shown in this logical diagram, where we can see that carry propagation is obtained as XORing of the two bits which we are going to add, while the carry generation will be obtained as ANDing operation of the two bits which are to be added. Now from this propagation and generation of the carry bits, we are having the generation of the sum output and carry output for that full adder circuit. So this sum output is going to take the carry propagation and carry in for that particular stage. It is going to XOR those bits, and that XORing output will be presented as that stage sum output. While to generate the carry output for the next stage, it is going to take the carry propagation, the carry in for that stage, those values will be ANDed. The ANDed result will be again going to get ORed with the carry generation of the previous stage, and here the next stage carry will get generated. Now let's look for how this particular carry propagation and generation block of logic diagram has got prepared. And for that we have to go for again the truth table of the full adder. Whether I am using a truth table for 4-bit or single bit, that doesn't matter, because we are going to do the operation of a single bit addition at a time when we are considering the parallel adders also. And that's why here we are taking 1 bit for each of the numbers in the multi-input numbers also. So we are having inputs as A, B and C in, while output will be sum and C out, as like for the full adder diagram. So here, as 3 inputs, we will have 8 number of input combinations for A, B and C in. Corresponding to these A, B and C in outputs, first the sum and C out column values has been specified by taking the reference of binary addition values for these resultants. Now we are going to divide these particular output corresponding to the generation of the carry and the carry where it is only propagated as like the input carry. So let's check for the first row. Here C out value is exactly similar to the C in. At the same time, in the second stage also, the C out value is similar to the C in value. That means here, for generating the output carry, no separate logic will be needed. And we are having the case that the output value for the carry is 0. That means in this 2 input combination situations, there will be no generation of the carry at the output side. While if we are observing for second, third, fourth and fifth stage, in all these stages we can observe that the output carry which has got generated is similar to the input carry. Next step, what we are going to observe is the third category, in which the 6th and 7th stage has to be presented, and it is going to show that in this the carry which is generated as C out is always equal to 1. So we can divide this whole truth table on the basis of the C out value, where it has got generated, where it has not got generated, and where it has propagated as like the input C in value itself. And based on that, now the previous circuit of this carry generation and carry propagation has been prepared. So in last stage, where we are saying the carry generation is needed. In the carry generation where it is needed, we can observe that the output carry value will be 1 only if both AB are 1, while Cin may be changing either as 0 or 1. And that's why to draw this logical diagram, we can say that carry generation is nothing but the ending output of A and B. While in the previous case of the carry propagation, we are observing that when either A or B is 1 and other bit value is 0, that time we are going to get the carry to be propagated from C in towards the C out. And this is nothing but the observation which we can have as the XORing of AB inputs. And that's why here we say that carry propagation will be generated by implementing the XORing operation of two bits to be added. And then we have named this GI as a carry generate signal and this PI as a carry propagate signal. So in previous slide also I have told you this PI is nothing but the carry propagate and GI is nothing but the carry generate. PI indicates the C out is to be carried as the value of C in itself, while GI indicates that the carry out value should be equal to 1. And again here the sum will be written as XORing operation of PI with the value of CI minus 1, because here first the carry propagate and carry generate has to happen. Then for the next stage the carry will be generated from the previous stage carry generate value or with the multiplication of the previous stage carry propagate and previous stage carry input value, which is indicated by this logical diagram. But this we have commented in general. Let's look for each individual place of the bit, how this carry generation and carry propagation is going to happen. And for that, first we will go for the C out that is to be generated, because this C out is going to tell us that for next stage what will be the generated carry. So C out is nothing but GI plus PI CI. So let's say that I am going to generate the carry out from first stage, but actually it is doing the operation for the LSB bit addition. That's why here I value will come as 0 for each of the G and this PC indication. For the next bit addition, which is A1 and B1, that I value will be 1, but we are writing the carry out for next stage, so it is C2. C2 is equal to G1 plus P1 C1. But C1 already we have obtained from this previous equation. Let's substitute this C1 value into this by replacing it. And when we will do this multiplication of P1 with this bracket, finally for C2 we can find it is a previous stage carry generation OR with the previous stage carry propagate, previous to previous stage carry generate, OR with previous stage carry propagate, previous to previous stage carry propagate, and the previous to previous stage carry input. In the same way, when I will go for addition of A2 and B2, the carry will be generated for the next bit, so it will be indicated as C3. That will be given by G2, that is current bits are added are A2 and B2. So current bit subscript will be 2. It will take G2 plus P2 C2. Again here for C2 From this previous equation, we will substitute the values and get the P2 to be multiplied. Then the equation we are going to get is given by here. Last bit addition will be A3 and B3. But that carry output we are writing as C4. So C4 will be written as G3, the previous bits, plus P3 C3. Here again for C3 we are going to substitute the values. So this value will be given as G3 plus P3G2 plus P3P2G1 plus P3P2P1G0 plus P3P2P1P0 and C0. So if generalized form of expression for the carry output to the next stage is to be written, then it will be given as, let's see everywhere, if I am adding the previous bits, the next bit carry is going to get generated. And that's why we will write the expression for C out as C of I plus 1. C of I plus 1 is nothing but this G of I. That means the current input value which we are going to add with the subscript of I. Then P of I, G of I minus 1. Next is P of I minus 1 and G of I minus 2. And so on if we are go on writing for these expressions. So I hope friends this expression writing is now clear to you. We will see the logical diagrams for these parts. But before that, we can say that in a carry look ahead adder operation of parallel bit, we will have three basic structures which are present. One is the carry look ahead generator, another is carry propagate and generate generator. Next one is the sum generator. So we can see here that when I will give the two inputs to be added parallelly, from that we are going to have a generation of a carry generate by ANDing of those two bits. For carry to be propagated, we have to have the operation which is to be done is XORing of A and B for carry propagate. For generation of the sum, we have to XOR the carry propagate and carry generate. In this way, from the previous equations, what we have written for C1, C2, C3, C4, from those equations here, we have obtained the C0, C1, C2 and C3. And finally, for the sum output to be written, we have used the Pi and Ci. So let's check for the sum of the A0 and B0 to be obtained. First G0 and P0 will be obtained. C0 is the input to this XOR gate and sum will be obtained as Pi and Ci to be XOR. So here XORing of P0 and C0 will be done. Similarly, in case of A1 and B1 addition, for A1 and B1 addition, carry generation and carry propagation will be given by this XORing and ANDing operation. Through that, G1 and P1 will be generated. C1 has been already generated from the this generator block of carry. This C1 is XORed with P1 to give the sum at the first bit position. In the same way, for the next bit positions, this addition operation has to be done. And that's why we are saying that in this carry look ahead structure, we will have this propagate generator, that is carry propagate generator, then the carry generator is present, and then the sum generator will be finally given out. So the next logical structure or combinational diagram that we are going to cover is the magnitude comparator. But please friends mind that here the digital values we are going to compare. And the digital values comparison means the 0 is compared with 1. And that's why we are saying here that this digital comparator is going to compare the value of two binary digits. And when we are comparing the two binary digits, there will be two types of digital comparators. And these digital comparators will be of two types based on how many number of output terminals it is having for expressing the comparison result. If I am having only one output terminal for expressing the comparator result, then it is said to be identity comparator, in which it is going to generate the output based on whether A value is equal to B. That means two compared numbers are equal or not. If the two compared numbers are equal, then it will generate the output as high output, and if the two numbers are same, also it may generate the output as low. It depends upon the IC whether it is a bubbled IC or it is without the bubble IC. That means it is a active low output or active high output concept. Active low output means that output will be indicated when the output value is 0. But output value is indicated as a high when the output is marked as a 1. So that IC will be active high output IC or it is active low output IC. But through the identity comparator, only one output terminal we are having over for the IC, and it will exhibit the comparison result of only the process of equality. That is whether A is equal to B or not. And that A equal to B will be represented by logic high IC by setting that output to 1 and logic low IC by setting that output to 0. Let's go for the another type of magnitude comparator. This magnitude comparator will have three different output terminals as shown in the given figure. And these three different outputs will give the result for whether A value is less than B, A value is equal to B, or A value is greater than B. And this result comparison, when it is done, the corresponding outputs will be presented as 1. So let's say the provided value of A is equal to B. Then in that situation, the output which is presenting A equal to B only will be 1, and these two outputs of A less than B and A greater than B will be 0. But if the presented A value is less than B, then the output corresponding to A less than B is only presented as 1, while these two outputs will be 0. In the similar way, if the presented A value is greater than B, we can find out this value of output will be only 1 and these two will be 0. This is how the digital comparators are going to work. In detail, now we are going to check for the magnitude comparator. So first we will go for 1-bit magnitude comparator. For the 1 bit magnitude comparator again, a single bit, two inputs will be needed. And as it is a magnitude comparator type of circuit, so it will have specification of three outputs as A less than B, A equal to B and A greater than B. But we have said this as a single bit magnitude comparator. So only single bit two numbers will be provided. So let's check for the condition and the truth table writing for this magnitude comparator of 1 bit. So when 1 bit magnitude comparator I am providing, the possible input combinations will be presented over here with these 4 input combinations. Now let's take the input value as 0, 0. Here the magnitudes of A and B are same. That's why for the output which is indicating A equal to B, over there only one will be set. For these two the value will be 0. For the input combination of A value is 0 and B value is 1, as we are seeing here A is less, so A less than B corresponding output will be set to 1 and other two outputs will be set to 0. In the next case, when A value is greater than B, only the output corresponding to A greater than B will be set as 1, while these two outputs will be set as 0. Now, the next input combination where again A, B both are 1, that indicates that both are equal. So, the output corresponding to A and B to be equal will be presented as 1, while other two outputs will be presented as 0. To convert this truth table into a logic diagram, we have to take the help of K map. And that's why here, corresponding to each output column, the separate K map will be written. And this K map should be of two variable because we are having two inputs for each of that circuit to be generated. So let's check for the K-map simplified output in the form of Boolean expression from this first column to be used out. The first column corresponds to the output of A less than B, where we are seeing when both A and B are 0, 0, output is 0. When A is 0, B is 1, output is 1. And again for other two input conditions, the output is 0. So that has been specified over here in this K map. So after simplification, by doing the group of this single one, we will find this resultant of output presenting as y1 is equal to a bar b. Similarly, we will write now a k-map of two variables of a and b for this y2 output. Let's check. When a and b both are 0, output is 1. Similarly, when both a and b are 1, at that time output is 1. That has got presented. Here in the adjacent cells, the ones are not present. So grouping we can't do even though there are two number of ones. So corresponding to each of that mean term, we will write down this Boolean, simplified Boolean expression, and it comes out as a bar b bar OR with ab for a equal to b. Then the third column of A greater than B related output we have to consider, which is presented in the K-map form of two variables, where we can see the output is 1 only if the A value is 1 and B value is 0. Corresponding to that presentation will done here. And based on that, the simplified output for this K-map which is obtained is A B bar. Then we are going to draw a circuit diagram by using the logical gates from these three obtained simplified K-map outputs. So the first y1 output corresponding to a less than b is needed as a bar b. So a is taken, it has got inverted, then b is taken, those two will be ANDed. So here the output corresponding to a less than b will get generated. The next stage is the output corresponding to a equal to b. And to generate that, we will need a bar b bar to be ORed with ab. So here we can see the first ANDing gate, which is going to take the two complemented inputs of A and B. So AND gate resultant will be A bar B bar, while this third AND gate takes the two input which are the original inputs A and B. They are going to be ANDed, AB will get generated, and here after getting the A bar B bar and AB, we are going to have this ORing operation to generate the final result of output for A equal to B. In the third stage, we are going to draw the diagram for the condition of A greater than B. And to obtain A greater than B, we will have original input of A but the complemented input of B, those are to be ANDed, which is presented by this fourth AND gate over here in this given diagram. The same diagram can be simplified with the less number of gate uses as shown in this particular figure. That means here, instead of using two separate AND gates and one OR gate, it has been simply implemented by applying only a single XOR gate. This is a simplified diagram of 1-bit magnitude comparator digital logic circuit representation. Now we will move towards the 2-bit comparator. That means here each of the number which we are presenting for the comparison is consisting of 2 bits. So we are having here A is represented by 2 bits as A0, A1 and B is represented by the 2 bits as B0 and B1. So we will find out that totally on the input side of this 2-bit comparator, 4 inputs will be existing, but as we are going to do magnitude comparison, so output again will be only 3 bits. That is the condition of A equal to B, A greater than B and A less than B. And now we have to obtain the truth table for the comparison result. And in the truth table, the number of inputs as we have specified here will be 4, while the number of outputs will be 3. So that we have mapped in these columns. Let's take the different combinations of the inputs, in which as each of the number is of 2 bits, so there will be 4 possible combinations for each number to be represented. And to write that, first we will consider that when the B1 and B0 are taking 4 different combinations, that time A0, A1 are remaining constant. And according to that, for the first 4 rows, we have kept A1, A0 constant with 0, 0, but B1, B0 we have changed from 0, 0, 0, 1, 1, 0 up to 1, 1. Then, once the 4 times changes of B1, B0 has been obtained, we will change the value of A1 and A0 as 0, 1 and we will keep that 4 times constant to get the B1, B0 values to be changed. So with corresponding to these 4 constant values of A1, A0, B1, B0 values have got changed. Once these 4 changes of B1, B0 will be obtained, next change we have to first apply to A1 and A0 with the magnitude of 1, 0. So 1 0 will be kept constant for 4 times. But in those 4 times constant value of A1, A0, B1, B0 will be changed from 0 0 up to this 1 1. And finally, the last A1, A0 combination to be applied is 1 1. 4 times again it has kept constant, but here B1, B0 we are changing from 0 0 up to this 1 1. So, is it clear, friends, how to write down the input combination for 2-bit comparator inputs? We know each number is of 2-bit combination, so possible combinations will be 4. So 4 combinations of A has to apply individually the 4 possible combinations of variations of 2 bits of B, and that's why totally 16 possible number of combinations in this input we are going to observe. Now let's check the output writing for this all possible 16 input combinations. So here we are finding that A0 is equal to B0, A1 is equal to B1. That means all the bits are equal, and that's why here for Y2, which is indicating A equal to B, the output will be set to 1 while other two outputs will be set to 0. Now in the case of A0 is now less than B0, but A1 and B1 are 0. In this situation also this A value is less than B, and because of that this output corresponding to A less than B will be set to 1 while these two outputs will be 0. Consider the next case in which A0 and B0 are same, so it doesn't matter, but A1 value is less than the B1 value. Because of that, here in this situation also A is less than B is true, so that will be set to 1 while other two outputs will be 0. The next step what we are going to observe is here A1 and A0 both are 0 while B1 and B0 both are 1. But if we are observing here both A bits are 0 and both B bits are 1, obviously A is less than B. So again it is set to 1 for the output of A less than B, and other two outputs will be 0. Next we will go for the combination of A1, A0, B1, B0 as 0, 1, 0, 0. Compared to B0, A0 is greater and A1 and B1 are 0, that is equal, but A1, A0 is greater than B0, so here the output A greater than B is set to 1 and other two outputs are 0. Now in the case of this input combination of 0 1 0 1 where we are observing A0 equal to B0 and A1 equal to B1. So in that situation the output corresponding to A equal to B will be 1. Other two outputs will be 0. Next input combination in which A0 is greater than B0 but B1 is B1 is greater than A1, and in this situation the number at which the MSB is 1, that number will be greater, and with this rule the MSB of B is 1, that's why here the B will be greater as compared to A, even though A0 value is 1. So A less than B is set to 1. Next operation in which we are finding A0 and B0 are equal, but we are finding that MSB of B is greater than LSB. If LSBs are equal, we have to look for MSB value comparison. And that's why here, as B1 is greater than A1, so we are writing the output corresponding to A less than B as 1 and other two will be 0. In the next combination, the LSB values A0 and B0 are same. So we have to look for MSB. MSB of A is greater as compared to MSB of B. And that's why this will be set as A greater than B, while A equal to B and A less than B will be set to 0. In the next combination, we are finding that MSB of A is greater as compared to MSB of B. So, even though LSB of B is greater than LSB of A, but we are finding that MSB of A is greater than MSB of B, so A is greater than B will be set. In this next condition, we are finding both LSBs are equal as well as both MSBs are equal. So it will set for A equal to B. In next case, we are finding that both MSBs are equal. Both MSBs are equal. But if the MSBs are equal and we have to compare, then we have to look for LSB value. And in that, LSB value of B is greater, so B is greater than A will be set. In the next condition, for both the positions of LSB and MSB, A is greater as compared to B. So here the final output set will be A greater than B. In the next input combination of 1101, A and B at LSB are equal. So if they are equal at LSB, we have to look for MSB values, and MSB value of A is greater than MSB value of B, and that's why it will be written as the output 1 for A greater than B. The same situation is going to be checked out in the next input combination, where the LSBs are compared. LSB of A is greater, but MSBs of two numbers are same. So based on LSB greater value, we can comment that A is greater than B. So A is greater than B, corresponding output will be set. In the last condition, both LSBs and both MSBs are equal, and that's why we are concluding that A is equal to B. And here we are generating the output of 1 for A equal to B. So in short, we can comment that if both the bits are equal, then only the output A equal to B will be generated with 1. Let's check here the situation. Here A equal to B is presented when both the bits are 0, 0. Here that is presented when A0 is equal to B0 and A1 is equal to B1. Similarly, in this situation, A0 equal to B0 and A1 equal to B1, and in the last also both the bits are equal. Then only we are presenting A equal to B output to be 1. But for the greater than conditions to be obtained, we have to check the two combinations. The greater than output for A greater than B will be set if A1 value is 1 and B1 value is 0. This is the first condition when the greater than output will be true. The second condition is when A1 and B1 are same and we are finding out that A1 and B1 are 1 or A1 B1 are 0 and A0 is 1 and B0 is equal to 0. So there will be two combinations in which we can find out this A value is greater than B. Either I will have both the values of A1 B1 should be 1, or I should have A1 B1 equal to 0, and at the same time the A0 value should be 1 and B0 value should be 0. Then the value of A is greater than B. So let's check for this condition. Here both A0 B0 are equal. Here both A1 and B1 are equal and A0 is greater than B0. In this condition, we are finding that A0, B0 are equal but A1 is greater than B1. Here, we are finding the condition that A0 is 0, B0 is 1, but in that situation, A1 is 1 and B0 is, A1 is 1 and B1 is 0. So it is said to be A greater than B. In this situation, A0 and A1 both are greater than B0 and B1 sequentially. In this situation, we are finding that A1 B1, out of that A1 is greater and A0 B0 are same. In the next situation, we are finding that A1 B1 are same but A0 is greater than B0. So it is set to 1. The case when A is less than B output will be safe. For that, we are having two possible combinations that we have to check. If suppose both MSB bits are equal, but in the LSBs I am finding that the B0 value is 1 while A0 value is 0. Then in that situation the less than condition will be set. Now again, from this given whole truth table, we have to write down the K-map to obtain the logical diagram. And the K-map is separately written for Y1 output, Y2 output and Y3 output. And the K-map which is written should be of 4 variable K-map, because we are having 4 inputs which are specified in this truth table. So let's start with writing the K-map for A less than B value. So A less than B, we are presenting B1 and B0 on the column variables and A1 and A0 as a row variables. So let's take the values. That will be 0, 1, 1, 1. So 0, 1, so we are mapping 0, 1, this one over here and then this 1. The next 4 bits which are taken are 00, 11. So here 00, 11. Next mapping, what we have to do is for this third stage, that third stage we are writing as the last elements. So those are all 0, 0, 0 and then 0, 0 and 1. So let's check. In this, the next row all elements are 0 and in the last row it is 0, 0, 1, 0. After doing this, we have to group the adjacent cell once. So we have possibly this first group of 4 ones to be grouped. Then the 2 adjacent ones are to be grouped, and finally this one and this one as a pair we are going to group out. So after simplification of this particular 4 ones to be obtained, we can find that as B1 and A1 dash. B1 and A1 dash. While for this group combination, we will find it as B0 and A1 dash A0 dash. B0, A1 dash and A0 dash. Now we will go for this pair simplification. So in the pair simplification, we will find out the output A0 dash is common along with B1, B0. So the mean term corresponding to that will be A0 dash B1, B0. Now we will go for representing the K-map for next output of Y2, in which we will find out 1000 to be mapped in the first row. So 1000 is mapped. Then after 1000 we are having 0100 that will be mapped. So 0100. Next to that will be last four elements first have to be written, which are 0001. So it will be mapped as 0001, and finally it is 0010. But we can see that at diagonal places the ones are present. That means we cannot get the grouping to be done for more number of ones. And we can write each of that term as it is. So here the first term will be A1 bar, A0 bar, B1 bar, B0 bar, while this second term will be written like this, third term will be taken like this, and fourth mean term will be presented like this. Now this particular part we can re-simplify, and finally we can write that this is a combination of A1 XNORed with B1 and A0 XNORed with B0. So after doing all these algebraic operations, you can find out the final result for Y2 is given by two XNORing operations ending to be performed. And finally, we have to present the K-map for this last column of the truth table, which is presented for A greater than B condition. And that A greater than B condition is presented into this K-map with the help of this presentation. Again, grouping of adjacent ones will be done and simplification form will be written. After getting the three simplified equations of A less than B, A equal to B and A greater than B, we have to go for drawing this diagram. So here friends, today we will stop, and in this total lecture we have completed the concepts of parallel adder, the carry look ahead generator, advantages of carry look ahead generator circuit. Then we have seen the comparator, but the digital comparator will be of two types. One is identity comparator with only one output setting as 1 or 0 based on equality condition of presented 1-bit number. Then we have gone for 2-bit comparator. Based on the truth table of 2-bit comparator, we have obtained the simplified circuit, and here we are ending today's sessions. So until then, bye and keep on learning.